Okay, we're going to try this, a look at solids. And for today, we're looking at different forms of solids. There are two main types of solid structures. They can be either amorphous or crystalline. An amorphous solid lacks a regular crystalline pattern. We'll be talking about crystals soon. But the property I think of with amorphous solids is that they tend to lack organization. They lack a regular melting point and boiling point. We've seen this in our classroom already. If you remember from the first week of school, we cut some glass tubing. And when we cut the glass tubing, there were sharp edges. Notice in green how these sharp edges could have been dangerous. So we softened our glass. We put the glass over a Bunsen burner and we started to heat it. It did not go through melting. There was no definite point where it melted, no definite temperature. Instead, it started to soften, and it started to soften over a broad range of temperatures. This allowed the molecules of silicon dioxide that makes up the glass to start to move, to roll over one another. And those particles, as they started to flow, tried to flow to the position of lowest energy, to make a sphere, to lower the number of surface particles. You can see how I've taken my purple line here, and I have shown how the glass would round on the edges. You experienced that in the laboratory. It was an amorphous solid. And not only does glass do this, but we might expect something like a wax, paraffin. Those things are also going to soften. If you have a candle, the wax softens. It doesn't suddenly change phases and go from the solid to the liquid. Okay? So this is one of the big differences in our different types of solids. The melting points. Is it a definite melting point like in water, where ice melts at 0 degrees Celsius? Or is it something like glass that softens over a broad range of temperature? The basic building block of all solids is going to be the unit cell. This is a basic repeating unit of what's called the crystal lattice. And the lattice, which I'll be showing you, is just a pattern of points. This unit cell is going to contain all the properties of the crystal lattice. And it's going to have 8 corners. Now, let's take a look at some lattice patterns. There are 7 basic crystal systems. And if you are using different textbooks for my classes, right now in Chang on page 448, in Zumdahl on page 446, you'll see some of the pictures, images of what I'm going to show you. So it's all right in that section. You would also want to read a little bit, if you're in AP, about closest packing. Closest packing. And if you're interested, you might want to look at how crystals are studied through X-ray crystallography, X-ray diffraction. Something that comes in there is the Bragg equation. Lambda is equal to d sine theta, which we used in one of our previous labs. Go back and check. But let's look right now at some of the 7 basic crystal systems. And within them, we're going to see 3 different kinds of lattices. Okay, here's going to be our simplest. The simplest is going to be something called, cubic. I wonder why. Now, if this is a cubic unit cell, let's look and see why it's called cubic. A equals B equals C. All the sides of the unit cell are identical in length. And lambda, let me see, what do they call these? Alpha is equal to beta is equal to gamma. All of the angles are the same. And as you can see within this unit cell, all the angles are 90 degrees. This is a basic or primitive unit cell. look at how this cubic cell is different. I know you can see it already. You have the 8 points at the corner, just like in a basic unit cell, a simple unit cell, or a primitive unit cell. And yet here, not only do we have the 8 corners, we have an additional particle in the center. These corners, these particles could be atoms, ions, or molecules depending on the substance. Now, let's talk about the difference in these 2 unit cells. It's kind of hard to see if you're looking in one dimension. How many particles make up this 1 unit cell? This particle right here does not totally belong to this unit cell that I'm showing you. You have to imagine in 3 dimensions that there is another unit cell sitting here, like here, another one here, another one here, 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 and here. This particular particle belongs to 8 unit cells. Only 1/8 of this corner belongs to this unit cell. So if 1/8 of this particle belongs to this unit cell, and there are 8 particles, this unit cell really is made up of 1 particle. This unit cell is different because the corners, 1/8 of each corner belongs to this particular unit cell, but the one in the center belongs totally to this unit cell. 2 particles belong to this unit cell. And it gets even more complicated. Look at this. Face-centered. Face-centered. Cubic. Because not only do you have the particles in the corners, in the middle of each face, there is another particle. 1/8 of each corner belongs to this unit cell, and 1/2 of each face belongs to this unit cell. So, if you have 6 faces and 1/2 of each of them belong to this unit cell, 3 particles total come from the face particles, and 1/8 times 8, 1 particle comes from the corners. 4 particles would make up this unit cell. Different layers of complexity. Simple, cubic, body-centered cubic, face-centered cubic. There's lots of variations on a very simple starting point. I think solid crystals are very difficult to master. It takes someone who wants to specialize in this area. And yet, you can know something, you can learn something about solids by just studying the basic building blocks. Let's look at some other variations. For example, here is a structure that A is equal to B. Whoa-ho! But it's not equal to C. So when we look at this, this is a tetragonal structure. All the bond angles are still 90 degrees. So this is called simple tetragonal or primitive tetragonal. What would we call this structure? Body-centered tetragonal. Okay. And then let's look at this one. This is an illustration where A does not equal B, does not equal C. All of these sides are different, but bond angles are still 90 degrees. And this is called orthorhombic. Simple or primitive orthorhombic. How can we see variations on this structure? What would these be called? body-centered, face-centered, orthorhombic. And how about this? More variations are out there than what I'm showing you. This isn't body-centered or face-centered because there is nothing at the faces. They are only at the top and bottom additional particles from the corners. This is called base-centered orthorhombic. Bases. Only on the base, top and bottom, do we have additional particles. How many particles belong to this unit cell? 1 from the 8 corners, 1 from the 2 bases, 2 total. And of course we can get more complicated if we wanted to look at things like, let me make sure I've got them right. How about this one? The first thing that strikes you is that this is not going to have 90-degree angles. But, picked up the wrong one. I think this one's probably better. Here we go. But all of our sides are identical. All the sides are identical. And this is called rhombohedral. A equals B equals C, but bond angles are not 90 degrees. Here, you can see a little bit of a variation in that A equals B, but C is very different. Bond angles do not equal 90 degrees in all cases. And so this particular type of unit cell is called hexagonal. These are in your textbook. And the last one would be here where A does not equal B and does not equal C. There are bond angles other than 90 degrees here. And this particular unit cell is called, let's see, this is called monoclinic. So, these also have variations which could be body-centered or face-centered. What is going to determine what unit cell is going to be formed? Let's take a look. In your book you see the 7 basic crystal systems like cubic or tetragonal or rhombohedral. You see the 3 kinds of lattices like simple or primitive, body-centered, face-centered. But what crystal is going to form is going to be determined primarily by 2 things: the relative size of the ions and the ratio of cations to anions. If you're looking at rock salt as your example, this is going to have a face-centered cubic structure. And you need to know that. NaCl is face-centered cubic. You should know bond angles, you should know lengths at this point of the sides. The ratio of Na to Cl is going to be 1 to 1, 1 sodium to 1 chloride. And that's what allows it, the size of the atoms and the ratio of the positive to negative ions allows it to form this type of crystal. If you had calcium chloride, it could not be the same unit cell. It would have to be different. So, this gives us some idea of what we're looking at when we talk about crystal structure. And so all you have to do is just learn it. Study what you can. There's not going to be a lot of class time that we're going to spend on solids. So you can read a few pages in your textbook. How much of this do you need to know? But in the next video, we're going to be looking at solids again. And that's going to be something we'll focus on, even in class. Work hard. Thanks very much.